In this video, we're going to go through Hess's law. So Hess's law states the enthalpy of a given chemical reaction is constant regardless of the reaction happening in one step or many steps. So here are the key ideas. Reactions must add up to the target reaction. So we're going to add up all of the different steps, and the enthalpy values must add up to the target reaction. If you reverse a reaction, meaning you switch the reactants and the products, the sign for delta H will also flip, but the magnitude stays the same. You'll see what you mean here when we do a practice problem. If you multiply the change coefficients to match the target reaction, you must do the same to the delta H value. And again, you'll see what we talk about here when we do an example. Okay, so here is our first example. It says, given the following data, calculate delta H4. So the reaction given, this is what we want everything to look like. Okay, that reaction right there. And then we have two steps. Now, some things to consider. Anything that exists on the reactant side and the product side will cancel out. So if you look at the given reaction, we have solid carbon on the left side of the reaction. Okay, we have solid carbon on the left side of the reaction here, and it only exists in that first reaction. So we don't want to flip the first reaction because we want to keep carbon on that side. Okay. We also have, let's see, we have CO2 gas. So I believe this is supposed to be gas here. That's on the reactant side. We need it to be on the other side of the reaction. So we're going to need to flip this reaction. Okay, and in doing so, we are going to change the delta H value. Okay, so I'm going to rewrite both reactions very quickly here. All right, so that one we don't want to change. The second one we want to flip. Okay, so now watch what happens. CO2 exists on both sides of the reaction, so I can eliminate it. And if you look in the reaction we're looking for, our target reaction, CO2 isn't there. So great, that goes away. CO, carbon monoxide, is in the product side of our target reaction, and that's where it's supposed to be. Carbon solid is in the reactant side. In the target reaction, that's where it's supposed to be. But we have this 1/2 O2 in the target reaction. And if you look here, it's only on the product side. Well, I can get rid of the half oxygen here, and there's an imaginary 1 in front of the O2 here. So if I cancel half of that 1, I will be left with 1/2. Okay, so now let's do the math. So we flipped the second reaction, so that side is going to flip. So instead of being negative, that'll be positive. So let's do the math here. So we had negative 393.5, and we're going to add that with 283, and we get a value of negative 110.5 kilojoules. That's it. Remember, if your delta H value is negative, it is exothermic. Okay, let's do another example here. It says, given the following data, calculate delta H4. Okay. So, same thing. I'm going to look at the target reaction here, and I want to look for the pieces that I want. So, we've got 2 NO. So, oh, geez, we have NO everywhere here. Well, let's see, we have 2 NO here, and that's 2 NO2. Okay, so the NO is in the second reaction, and it's already on the correct side of the reaction, so I don't want to flip that one. I want to leave that one alone. We also have O2 in the target reaction on the reactant side, and it's on the reactant side in reaction number 2, so I want to leave that one alone. Now, N2O4 is on the reactant side in reaction number 1, and we want it in the product side in our target reaction. So we're going to need to flip our first reaction. So this will now be negative when we do our calculations. So let's go ahead and rewrite that. So we have, let's see, 2NO2. Okay, and that will go 2N2O4. So that's for equation number 1. And equation number 2, we have 2NO plus O2. And that goes to 2NO2. Okay, so let's get rid of what's on both sides. So the NO2, the 2NO2 is on both sides, so we can cancel that out. And look at that. If I rewrite this, we have 2NO plus O2, and that goes to N2O4, which is what we are looking for. So let's do the math here. So remember, we flipped the sign on the first one because we flipped the reaction. So this will be 57.9, negative 57.9. And we're going to add that to 113.1, and we get a value of 55.2 kilojoules. All right. Okay, so now let's look at this. So we have 3 reactions here, and it says calculate the enthalpy change for the reaction below. So this one is going to be a little bit more involved, so let's go ahead and add another page to work here. Okay, now the target reaction is down at the bottom this time. So here's our target reaction. Okay, so the way that I'm going to approach this is the exact same way. I'm going to look for the species in the target reaction in the different steps and figure out what I might want to flip. Okay, so let's see. Let's start with NO2. So let's see, I've got NO2 here. I have, okay, so NO2 is only in our first reaction, but it is on the wrong side. So we're going to need to flip the first reaction. And let's look at the second one, so H2O. So H2O is in the second reaction, and it's on the correct side, so we don't need to flip anything. But we have a 2 in front of it, so we'll need to address that in a second. Okay, let's look at HNO3. HNO3 is supposed to be on the product side, and it is on the product side of our second reaction, so that's good. Okay, and we've got one more. I'm running out of colors here. All right, we've got nitrogen monoxide, NO. That is in the first reaction here, okay, and it is also in the third reaction. Okay, so what do we need to do here? Well, here's the problem. We know that we need to flip the first reaction. Okay, we know that we need to flip the first reaction. We've already addressed that here. Now, if I flip the first reaction, nitrogen monoxide will be on the product side, and we're going to have nitrogen monoxide on the product side in both cases, the first and the third reaction. They're not going to cancel, and then we have some coefficients here. Okay, so let's do this. We're going to flip this. Oops, I'm sorry, we're not going to flip that one. We haven't said that yet. Let's rewrite these flipped. Okay, so the first reaction we're flipping, so that'll be 2NO2. Okay, and that'll give us 2NO here and O2 for the first reaction. For the second reaction, we are going to have 2N2 plus 5O2 plus 2H2O, and then we'll have 4HNO3. Sorry, my stylus stopped working halfway through the last video. So to do this with the mouse, the old-fashioned way. All right, third reaction. We have N2O2, and then that goes to 2NO. Okay, so let's look and let's see what cancels, if anything cancels. We have a couple things like O2, for example. O2 is not in the target reaction, so we want all of the O2s to cancel. Okay, so right now I have 6 O2s. 6 O2s. I have 1 here, 5 here on the reactant side, and I only have 1 to cancel right here. So we need to make those all go away. Also, we have a 2 in front of our NO2, and we want that to go away because in the final reaction we have a 3. So what times 2 makes it a 3? So if I multiply that, let's multiply this whole thing, and this is going to get a little ugly. Let's multiply the whole thing by 3 halves. If I multiply the whole thing by 3 halves, I'm just going to replace this. This will turn into a 3. This will turn into a 3. Okay, and then this will turn into a 3 halves. Okay, so we flipped it and we also multiplied it by 3 halves. Okay, so we did that. All right, that doesn't really help us with the oxygens though, because we still have a giant mess of oxygens here. Okay, so let's look at the second reaction. In the second reaction, we know that we want to turn our H2O into 1, because if you look in the final reaction, it is a 1 H2O. So let's do the same thing. Let's multiply the whole second reaction. To get rid of the 2 and make it a 1, we're going to multiply this whole thing by a half. So going to make that note up here that we multiplied it by a half. So that would change our 2 into a 1. That would change, 5 halves. Let me just move this over, so that'll make this 5 halves. Okay, now if you don't like fractions, you're probably getting a little nervous right now because we've got some fractions going on, but don't worry. Okay, half of 4 would be 2. And this is a pretty difficult problem. Okay, so we multiplied everything by a half. That's where we ended up. Okay, so right now, let's take a look at what happened. So 3 halves. So 3 of the 5 halves will cancel here, and we'll just be left with 1. And then we have another 1 right here. So we're close. We're close, but we also need to address this here in just a second. Okay, so we basically want the oxygens to all go away. So we want this to be a number that will cancel out. So when we cancel, so we have a 3 here, we have a 5 here. We basically need another 2 halves on the right side to cancel. So what if we flip the third reaction? Let's flip the third reaction. So let me rewrite this really quick. Like I said, this is a challenging problem. So when you're working Hess's law problems, you might have to go back and forth. You might change something and realize that it's not correct. The first 2 problems that we did, super easy, no problem. This one is a little bit more involved. Okay. So I'm going to make this a little bit easier for those of you that don't like fractions. So we know there's a 1 here, and that is the same as, I could rewrite that since we're working in halves. Let's rewrite that as 2 over 2. Okay. So now 3 halves plus 2 halves is 5 halves. So now we can cancel all of the oxygens. Those all go away. Well, what else will cancel out? We don't want to have any N2s in our final reaction. We don't want to have any N2s in our final reaction. So Does that cancel with anything? Let's see here. So we have N2 in this reaction here. We have N2 in this reaction. Yep, those will cancel out. Okay. What else do we need to have in our final reaction? We need to have 3 NO2s. So that's good. We've got our waters fixed. We want to have 2 HNO3s. That's correct. Now we need to reconcile our nitrogen monoxides. And we have that in 2 spots here. We want to have 1. There's 3 on the product side. There's only 2 on the reactant side. So I can get rid of all 2 here. And if I do that, I will be left with 1 of these. So I know this looks like a giant mess, but let's go ahead and rewrite it. So we have 3 NO2s here. Okay. We have our 1 water here. Okay, what else do we have? We have our 1 nitrogen monoxide. And then we have our 2 HNO3s here. Okay, now we want to multiply the first reaction by 3/2 and then switch the sign. So let's do that on our calculator. So we want to do 3/2 times, let's flip the sign, so this will be positive 1/16. Okay, so we've got that. We want to multiply the second one by 1/2, so 0.5 times, we want to keep the sign intact, so this will be negative 256. Okay, and then the last one we want to switch the sign. So instead of adding 183, let's subtract 183. And we get an answer of negative 137. So our delta H here would be negative 137 kilojoules. Okay, so like I said, that last problem was a little bit more involved. The first 2 problems were just kind of to warm me up, but just remember the rules. You want to make sure the reactions add up to the target reaction. So every single time we took the steps, flipped them, multiplied them, and we wanted them to add up to the target reaction. Anything that exists on both sides, we can cancel out. If you reverse a reaction, you switch the sign, but we keep the number the same. So for example, in the first one, we flipped this reaction, so we flipped the sign, but we didn't change the number. It was still 283. And then finally, if you multiply to change the coefficients to match the target, you must multiply the delta H value. So that kind of came into play in the third one. So we had to multiply the first reaction, for example, by 3/2. So we took our delta H value and we multiplied that by 3/2 as well. And that's Hess's law.